Hello, this is Dr. Armand again, bringing you another exciting lecture in general chemistry. Today we'll be talking about electrochemistry. So the main things here are looking at what an electrochemical cell is, looking at how to balance redox reactions in acidic and basic solutions, and then finally discussing cell potential and how to calculate cell potential of electrochemical cells. And how do we know if a electrochemical cell or a electrochemical cell is spontaneous or not. So sit back and relax and enjoy the show. So electrochemistry is divided into two parts. The first part, as I discussed at the intro. The second part, we'll be looking at calculating the cell potential using the equilibrium constant, and also calculating the cell potential at non-equilibrium conditions, and then finally finishing off with electrolysis or electrolytic cells. So first we're going to look at a few review questions from the previous chapter. So for this question, I think I should rephrase it. We want to determine what is the delta S, the value, the sign of delta S for each of these processes. So we have these different processes, and we want to determine what the delta S is for it. So this is a little bit weirdly stated, but here we want to determine the sign or predict the sign of delta S. It's either going to be positive or negative. So we have lithium chloride in solution becomes lithium solid. So again, lithium is a group 1 cation. So when it's in solution, it has more entropy than when it's a solid. So here the delta S of reaction would be negative. Next, we have the sublimation of I2 solid to I2 gas. So since you have a gas on the product side and a solid on the reactant side, entropy increases because the gas is more entropic than a solid. So here the delta S would be positive. Next, we have the synthesis of calcium carbonate. So we have calcium oxide plus CO2 gas gives us calcium carbonate. And again here, since we have 1 mole of gas on the reactant side, 0 moles of gas on the product side, delta S would be negative. Next, we have iron 3 nitrate. Aqueous goes to iron 3 nitrate solid. Since iron is a very small, highly charged cation, it's going to be more ordered in solution than as a solid. So since we're going from aqueous to solid for iron 3 nitrate, it's going to increase entropy because again, iron 3 plus is a small, highly charged cation, so it's going to order or arrange the water molecules around them. So as we go from aqueous to solid, in that case, we increase entropy. Next, we have CO2 gas to CO2 aqueous. So again, you have 1 mole of gas on the reactant side, no moles of gas on the product side. So entropy is going to decrease. So delta S is negative. Next, we have the decomposition of dinitrogen tetraoxide. Gives us O2 and N2. Here, delta S is going to be positive because we have more moles of gas on the product side versus the reactant side. So here the predicted sign of delta S is positive. And then finally, the freezing of water to ice. We're going from a liquid to a solid. So delta S would be negative. So that's how you predict the sign of delta S. You look at your reactants to products and see if entropy has increased or decreased. So here again, now we have chemical reactions. We want to determine or predict the sign of delta S. So again, we have the synthesis of potassium perchlorate. You'll see on the reactant side we have 1 mole of gas. On the product side we have no moles of gas. So the delta S would be negative because we go from 1 mole of gas to no moles of gas. Next we have the reaction of sodium and water. We form aqueous sodium hydroxide and hydrogen gas. So now you'll see that there's a gas on the product side, no gases on the reactant side. So here delta S would be positive. We condense steam into water, so we're going from a gas to a liquid. So delta S would be negative. Next, we're going to dissolve ammonium nitrate and get ammonium and nitrate ions. Since ammonium is a very soluble cation and is not very highly charged, it's going to increase in entropy when it goes from a solid to aqueous. So here, delta S would be positive. Next, we have the combustion of methane, produces CO2 gas and water. So since we have 3 moles of gas on the reactant side, 1 mole of gas on the product side, here delta S would be negative because we have fewer moles of gas on the product side. Next, we take N2 gas, put it in solution. So we're going from a gas to aqueous. Here delta S would be negative. And so the ones that have positive delta S are D and B. And then one last practice question. We're given this reaction, and what can be said about delta G? And if we remember, delta G equals delta H minus T delta S. So in this reaction, we know that delta H is negative because it's exothermic. And the reason it's negative is because it's exothermic. Now, if we look at delta S, we have 6 moles of gas on the reactant side, 3 moles of gas on the product side. So here delta S would be negative as well. So what happens is delta H is negative and delta S is negative. So since delta S is negative, the negative T delta S becomes positive T delta S. And so as long as T delta S is less than delta H, it's going to be spontaneous. So this would be spontaneous at low temperature and non-spontaneous at high temperature. Because again, this negative T delta S becomes, these two negatives make it a positive. And so as long as T delta S is less than delta H, the magnitude is going to be spontaneous. So this is spontaneous at low temperatures, non-spontaneous at high temperatures. And so this is just kind of a review from the chapter on spontaneity and free energy. Now we're going to shift gears and talk about electrochemical cells. So introducing electrochemistry. And electrochemical cells are based on redox reactions involving the transfer of electrons. You may ask, why are electrochemical cells important? They're important because they're found in every battery that we use. So every battery that you use involves the transfer of electrons. They're called electrochemical cells. Now, there are two types of electrochemical cells. We're going to spend maybe 70% of it on one type, the galvanic cells, 30% on electrolytic cells. So the galvanic cell, as you can see, it's spontaneous. And if it's spontaneous, that means delta G is negative, and the system does work in the form of electrical energy on the surroundings. So this cell produces electrical energy. That's how a battery works. Now, electrolytic cells, as we'll find out later, they're non-spontaneous. So that means that delta G is positive, and you have to supply the electrical energy to do work on the system. So it's the opposite. And so these are the two types of electrochemical cells. And there are some main components that we have in these cells. So we always have an electrode, which helps conduct the helps move electrons from one side of the electrochemical cell to the other. And these two electrodes are called the cathode and anode. So cathode is where reduction occurs. That means something gains electrons. Anode is where oxidation occurs. It means something loses electrons. And so the cathode generally I should say, gains mass. Because if it's a solid cathode, say nickel, as you're doing more reduction, more nickel gets produced. It kind of clumps to the, and this is over time, I should say, over time. And the anode generally loses mass over time. Because as the anode gets oxidized, say it's, for example, aluminum, it gets oxidized, it loses mass because aluminum gets converted into aluminum 3+. And a good little saying to help remember what occurs at the anode and cathode is anox, meaning anode oxidation, and a red cat, reduction and cathode. Now, in addition to the electrodes, you got to have electrolytes. And these are solutions of ions that you submerge the electrode in for the electrochemical reaction to occur. Now, electrolytes are generally similar to the cathode. So, for example, if you're using a nickel cathode, you're going to have maybe a nickel 2+ solution. If you're using an aluminum at the anode, you're going to have an aluminum 3+ solution. So you need electrodes and electrolytes for electrochemical cells. And so this is the main, or showing you an illustration of both a voltaic cell and electrolytic cell. So voltaic cell, we release energy. It's a spontaneous reaction. The system does work. So here you see the anode produces the electrons. The cathode consumes the electrons. So the electrons flow from the anode to the cathode. So we have oxidation at the anode, reduction at the cathode for a voltaic cell. And then we have what's called a salt bridge, which we'll talk about a little bit later, that connects the two cells. And this is to help even out the charge of the solution. Now, electrolytic cells, energy is absorbed, and it's a non-spontaneous reaction. So you have to input power for the reaction to occur. And typically this is, you have anode oxidation. Typically this is an anion, like A-, loses an electron, becomes A. And then the cathode is where reduction occurs. But this is all in an electrolyte mixture of A- and B+. There's no salt bridge between them. And electrolytic cells are what they use sometimes to plate silver or gold on, for example, utensils or a watch. And so again, these are the two types of electrochemical cells: voltaic, which is spontaneous; electrolytic, which is non-spontaneous. So we'll concern ourselves now with just looking at voltaic cells. We'll talk about electrolytic cells a little bit later. And so for voltaic cells consist of half cells, which is one electrode dipping into an electrolyte solution. So we go back. Each one of these beakers is a half cell that contains an electrolyte and electrolyte solution. Oops, not that. Oops, escape. Now there are two types of electrodes for voltaic cells. We have inactive electrodes and active electrodes. So inactive electrodes are used when there's no reaction components that can be physically used as an electrode. So for example, if the cathode is say iodine, you can't physically use iodine as an electrode. So then you would have to use something like platinum or carbon graphite. And these electrodes do not involve themselves in the reaction. They're just there to help facilitate the transfer of electrons. Now, active electrodes are actively involved in the redox process. So these are things like, silver electrode, nickel electrode, pretty much any metal, almost, if it's a metal solid, is going to be an active electrode. Now, in addition to the electrodes for a voltaic cell, you need a salt bridge, which joins the two half cells, and it acts something like a liquid wire. And what you do is the salt bridge is actually submerged in both electrochemical cells to kind of connect them. And so the anions of the salt bridge flow to the anode. Because oxidation is occurring, it prevents the solution from becoming too positively charged, or helps replenish helps balance out the positive charge in solution from oxidation. Because as you oxidize, you generate more positive charge in solution. So the anodes flow in to help balance that charge in solution so it doesn't become too positive. It runs out of anodes. The cathode, the cations, flow to the cathode to help balance out the negative charge in solution from reduction. So as you're doing your reduction at the cathode, it's consuming the cations in solution, so the salt bridge brings in more cations to help balance out the negative charge from the deficiency of positive charge in solution. And if you don't have a good salt bridge, your electrochemical cell will not work. This is a very common issue in electrochemistry lab, at least when I've taught it. When you don't have a good salt bridge, after a few seconds or a few minutes, the electrochemical cell stops working because you got to have that salt bridge to balance out the ions. So this is an example of an active electrodes. So we have zinc and we have copper. Zinc is oxidized, so we lose zinc on the anode over time. Copper is reduced, so copper 2+ in solution starts acquiring those electrons and starts plating on the electrode. And so what you see over time is that the anode typically decreases in mass because you're consuming those zinc atoms to make zinc 2+ ions to give up 2 electrons. And then on the cathode, you'll start seeing it gain mass because the copper plates onto the electrode. because the copper 2+ ion gets the 2 electrons, forms copper, sticks to the surface of the electrode. So over time, the cathode increases in mass, the anode decreases in mass. And you notice the electrolyte solution, zinc 2+, when we're using a zinc anode, and copper 2+ when we're using a copper anode. You'll also notice that the anion in the salt bridge flows to the anode solution, and the cation in the salt bridge flows to the cathode solution. And your salt bridge is usually some group 1 salt, maybe like sodium sulfate, sodium nitrate, potassium nitrate, etc. Now, inactive electrodes are just there to help facilitate the movement of electrons. So here we have a reaction involving I2, or the oxidation of iodide, or the reaction of iodide and permanganate. And iodide is oxidized to I2. However, we can't use I2 as an electrode. So what we use instead is we use a carbon electrode, which is an inactive electrode. It is not involved in either the oxidation or reduction half reaction, and it doesn't show up in the overall reaction. It's inactive. On the other side, in the cathode, we have permanganate and manganese 2+. So permanganate gets reduced to manganese 2+, but manganese 2+ is not a solid, so we have to use again a inactive electrode such as carbon graphite to help facilitate the movement of electrons. And so again, inactive electrodes such as carbon and platinum do not appear in the half reactions or the overall reaction. They're just there to help facilitate the movement of electrons. Again, notice that the anion in the salt bridge goes towards the anode solution, and the cation in the salt bridge goes toward the cathode solution. So now you can imagine that it's very, tedious to have to draw the entire electrochemical cell for a electrochemical reaction. So what we do is we draw the shorthand notation for a voltaic cell. And so what we see here is that we have zinc 2+, copper 2+, and copper. And so typically if you have active electrodes, the active electrodes are going to appear on the outsides of the notation. So these are active electrodes. They always appear on the outside of the shorthand notation. Now, on the left side is the anode process or oxidation. On the right side is the reduction process or cathode. Now the two double lines shown here, this represents the salt bridge. Now, the single lines are used when the anode and the anode species, the anode solution, are different phases. So that's when you use the single lines. So again, on the left side is the anode compartment. On the right side is the cathode compartment. The double vertical lines indicate the salt bridge. The single vertical line indicates a phase boundary, because zinc solid is a different phase than zinc 2+. You use a single line. If they were the same phases, for example, using an inactive electrode, you would use a comma. So again, if the half cell components are the same phase, we separate them with a comma. When they're different phases, we use a single line. Now, one thing you got to remember, so for example here, we have an inactive electrode graphite, single line iodide, which is aqueous, I2, which is solid, another single line. The salt bridge, permanganate, H plus and Mn2 plus are all the same, so you see we use commas to separate them, and then a single line because then we have a graphite. So let me show you something here. This slot, which I've labeled these 1, 2, 3, and 4. 1 and 3 are reactants. Two and 4 are going to be your products. And that's how you can write the chemical equation based on the shorthand. So 2 and 4 are products in the redox reaction. So now we're going to look at some examples of how to write notation and also how to take the notation and write the chemical reaction. But again, the inactive electrodes do not show up in the chemical equation. So here we have some reactions we want to write the shorthand for, and then in part 2 we have some shorthand we want to write the chemical reactions from. So in number 1 we have aluminum plus chromium 3 plus gives us aluminum 3 plus and chromium. You'll notice here that aluminum is oxidized because its charge becomes more positive, and chromium is reduced because its charge becomes more negative. So the anode, I'll circle in red, is aluminum. So aluminum is the anode. The cathode is chromium. So these two should appear at the ends of the shorthand notation. So now if we were to write the shorthand notation, it'd be aluminum solid, single line, aluminum plus 3, aqueous, double line, chromium plus 3, aqueous, single line, chromium, solid. And that's the shorthand notation for this electrochemical cell. Next we look at B. We have copper 2 plus reacts with sulfur dioxide, to form copper solid and sulfate. The H plus indicates it's an acidic solution. So again, what we notice, we have copper is 2 plus, and then we go to copper solid. So that tells us that copper is reduced. And then we have SO2, where sulfur here is a plus 4, and in sulfate it's a plus 6. So SO2 is oxidized. So the cathode is SO2, the anode is copper. Now since SO2 is a gas, we're going to have to use an inactive electrode. So let's write this. So we'll use platinum. That's our inactive electrode, single line, SO2 gas, single line, excuse me, not SO. Single line H2O liquid, single line, SO4, 2 minus, aqueous, comma, because H plus is the same as SO4, 2 minus, H plus, aqueous, then our salt bridge, boom, boom, and then we have copper 2 plus, aqueous, single line, copper. And so that would be the shorthand notation for this electrochemical cell. Again, the way we know that sulfur is being oxidized, because in SO2, sulfur is a +4, and SO4 2 minus, sulfur is a +6. Now, so on the second example, we're going to write a balanced equation from the cell notation. So in the first one, well, we're not going to balance them. We're just going to write the equation from each cell notation, because we haven't talked about balancing yet. So in the first one, we have manganese solid, manganese 2 plus, cadmium 2 plus, cadmium. Remember, this is the anode. This is the cathode. Also remember that slots 1 and 3 are the reactants. So 1 and 3 are reactants. 2 and 4 are products. So the reaction would look like Mn solid plus Cd plus 2 yields, Mn plus 2 plus cadmium solid. And that would be the reaction for this electrochemical cell. Now we go to the next one. We have a reaction involving iron and nitrate. So you notice here that since we're using nitrate and NO, we have an inactive electrode. And so we can cross this out because it's not going to be involved in the chemical reaction. So again, slots 1 and 3 are reactants. I'll highlight those in red. 1 and 3 are reactants, and 2 and 4 are products. So now we want to write our electrochemical reaction. Fe solid plus NO3 minus aqueous yields Fe plus 2 plus NO gas. Notice that platinum is not involved in the reaction. It's just an inactive electrode. Now we're going to show how to balance these in just a moment, but these is how you take the notation and write the chemical equation. So here we want to write the shorthand notation for the following redox reaction. So again, from this, we see that we have nickel 2 plus, it goes to nickel. So that tells us nickel 2 plus is reduced. Magnesium goes to magnesium 2 plus, that tells us it's the oxidized. So magnesium is the anode. Nickel is the cathode. So these should appear on the ends of the cell notation. So any cell notation which doesn't have magnesium listed first, because this is going to be the cathode, the anode. So the anode is listed first, and then its solution, and then the cathode, solution, and cathode. So A and C should be at the ends of the notation. And A should be to the far left, the anode should be to the far left, the cathode to the far right in the shorthand notation. So you can already see A we can disregard because it has magnesium 2 plus on the far right. B has magnesium and nickel on the ends. C has nickel 2 plus on the far left. We can get rid of that, so it should be a metal. So we've negated A and C. D, we have magnesium 2 plus on one of the ends, so we can disregard that one. Now for E and F, it says nickel and nickel 2 plus and magnesium, magnesium 2 plus are the same phase. Well, obviously that's incorrect because they're different phases. Likewise for F, it says magnesium, magnesium 2 plus has a comma, which says they're same phase, but they're different. One is solid, one is aqueous, so we can disregard that. So just by the process of elimination, we see that the answer is B. Because magnesium is at the far left, which is the anode, nickel is the far right, which is the cathode. And they're all separated by single lines because they're different phases. Next, we want to take and write the chemical equation from the electrochemical cell. So what we have to remember is that since this platinum is an inactive electrode, we can disregard it. So every reaction that has platinum, we can omit. So we can omit B because it has platinum, C has platinum, and D has platinum. Because it's inactive, it shouldn't be in the chemical reaction. Now if we take a look, remember slots 1 and 3 are reactants. So we want to see manganese and chloride ion on the reactant side. So it's not A because it has magnesium 2 plus and chloride, so we can disregard that. Now it's not F because it has chlorine dioxide, not chloride. And so by process of elimination, we see that it is E. And so that's how we take cell notation and write the electrochemical cell. So now we're just going to look briefly on writing or balancing redox reactions by using the half reaction method. So what that does is it treats the oxidation and reduction reactions separately. And so we divide it into half reactions. So first step is we divide the skeletal reaction into its two half reactions. So we have to determine what's being oxidized, what's being reduced. We balance the atoms and charges in each half reaction. We'll talk about that with electrons. And so what happens is when the atoms are balanced, we balance them in this order. Atoms that are not oxygen and hydrogen, then the oxygen, and lastly, we balance the hydrogen. The charge is balanced by adding electrons. And we'll show you that as well. So those are the two steps, and then we may have to multiply so that the number of electrons gained is equal to the number of electrons that gain in the reduction or equal to the number of electrons lost in oxidation. And then we add the balanced half reactions and include the states of matter. Now we also, if it's basic, we'll have to do one extra step if it's in a basic solution as well. So let's look at some examples of balancing redox reactions. And then finally, we make sure that the atoms and charges are balanced in the overall reaction. So whatever the total charge is on one side has to be the same on the other. So let's delve into this right now. So you can balance it usually in two different solutions, acidic and basic solutions. And we'll start with acidic first because once you balance an acidic, the basic is just one extra step at the end. So here we have permanganate plus NO2 minus gives us manganese dioxide and nitrate. So first we need to determine what is oxidize and reduce, and the main thing you should remember is that oxygen has a -2 charge. So in all of these, oxygen is -2. Now by doing that, we can calculate the charge of the cation. So manganese is +7, nitrite, nitrogen is +3, manganese and manganese dioxide is +4, and or nitrogen and nitrite is +5. So now we can write the two half reactions. So we see that permanganate, MnO4 minus, gains 3 electrons to form MnO2. And again, this is going to be the reduction. So this is reduction. Okay. And then nitrite is oxidized. So NO2 minus yields NO3 minus +2 electrons. So we need to look at the non-oxygen hydrogen atoms. Well, manganese is 1 and 1. Okay, and nitrite and nitrate are 1 to 1. So there's no need to balance the non-oxygen hydrogen atoms. Now to balance the oxygens, which is next, we have to add water molecules. And so we see that on the reduction half reaction, and this is oxidation, that manganese, permanganate has 4 oxygens, manganese dioxide has 2. So we need to add 2 water molecules. Now the oxygens are balanced. On the oxidation one, we have 2 oxygen. On the reactant side, 1 oxygen on the product side. So we need to add 1 water molecule. So now the waters are balanced. Next, we need to balance the hydrogens by adding H+. So on the reactant side, since we have 4 hydrogens on the products, we're going to need 4 H+. And since we have 2 hydrogen on the reactant side for the oxidation process, we're going to need to add 2 H+. All right. Now we need to balance the charge. So you see we have 3 electrons on the reactant side, and we have 2 electrons on the product side. So we're going to need to multiply the first one by 2 and the second one by 3. And now our resulting reactions become 8H plus 2 MnO4 minus plus 6 electrons yields 2 MnO2 plus 4 H2O. We do the same thing with the oxidation half reaction. We multiply it by 3. We get 3 H2O plus 3 NO2 minus gives us 3 NO3 minus plus 6 electrons plus 6 H plus. Oh no. Let me do that again. So we have 3 H2O plus NO3 NO2 minus gives us 3 NO3 minus plus 6 electrons plus 6 H plus. Now notice here that the overall charge for the reduction part, we have 8H plus, 2 MO4 minus, 6 electrons. So the overall charge here on this side is 0. On this side is 0 as well. So that's good. For the next one, the overall charge is -3 on this side. We have 3, 9, and 6 is -3 on this side. So the overall charge should be the same on both sides. Oh no, undo. Can I undo that? Yes. So now what we got to do is we add the two reactions. Oops, undo. Can I undo that? Yes. And we're going to cross out what's the same on both sides. So here you see we have 8H plus, we have 6H plus. Well, this 6 can cancel out, and this 8 is reduced to 2. We have 6 electrons on the reactant side, 6 electrons on the product side. They cancel out. 3 water molecules on the reactant side, 4 on the product side, so only we have 1 left. So now we can write the balanced redox reaction, and we get 2 MnO4 minus plus 3 NO2 minus yields 2 MnO2 plus 3 NO3 minus plus H2O. And you got to check here to make sure everything is balanced. So the overall charge on I forgot the 2H plus as well. So 2H plus plus snap. 2H plus plus yeah. So the overall charge on this side is -3. The overall charge on this side is -3. And you'll see that everything is balanced as well. 6, 10, 9, 8, 14, 9, 13, 14, 2, and 2. And so this is the balanced redox reaction in an acidic solution. That looks like crap. Oh, snap. Oh, snap. So this is the balanced redox reaction in an acidic solution. Let's look at one more example in an acidic solution. So we want to balance this redox reaction in an acidic solution. We have gold plus selenite gives us gold 3 plus the selenite ion. This is an acidic solution. So we need to see what's being oxidized, what's being reduced. Again, oxygen here is always -2. So if you're ever in doubt, most of the time, like 99% of the time, or 98% of the time, oxygen is going to be -2. Can't go wrong. So if we look here, gold is a solid, it's 0. Gold here is 3 plus. Selenium is a +6. Here, selenium is a +4. So gold is being oxidized, selenium is being reduced. So we have SeO4 2 minus plus 2 electrons yields SeO3 2 minus. Again, this is reduction. Then we have gold. Gives us gold 3 plus 3 electrons. And this is oxidation. Now we need to balance the non-oxygen hydrogens. You see that they're balanced, selenium 1 to 1, gold 1 to 1. So now we need to balance the oxygens. Well, here there's 3 oxygens, the other side is 4, so we need 1 water molecule. Gold doesn't need anything, there's no oxygens. And then we need to balance the hydrogens, so we put a 2H plus on this side. Now we need to balance the electrons. So we need to multiply this one by 3, this one by 2. And we get 6H plus 3 SeO4 2 minus plus 6 electrons plus 3 SeO3 2 minus plus 3 H2O. Do the same thing with gold. 2Au yields 2Au plus 3 plus 6 electrons. So you see here, overall charge is 0. Here it's 0 plus 6 and negative 6. Here we have negative 2 overall charge and negative 2 overall charge. So the charges are balanced. So now all we got to do is add together the 2 reactions. All right. So the only thing that crosses out are the 6 electrons, and now we can add the 2 together. So we have 6H plus 3 SeO4 2 minus plus 2 Au yields 2 Au plus 3 plus 3 SeO3 negative 2 plus 3 H2O. And so you'll notice that the overall charge on this side is 0. The overall charge on this side, both sides are 0. So this is the balanced redox reaction. So these were in acidic solutions. Now we're going to look at 2 examples in basic solutions. Same thing, we're just going to add 1 step at the end. So here we have aluminum plus nitrite gives us aluminum, AlO2 minus, and ammonia. This is in a basic solution. So again, we have to determine what's being oxidized, what's being reduced. So aluminum is a solid, it's 0. Now oxygen, negative 2, negative 2. So nitrogen in this is a plus 3. Aluminum is a plus 3. And nitrogen, if hydrogen is a plus 1, which it is, nitrogen is a negative 3. So nitrogen is reduced. Aluminum is oxidized. So we have NO2 minus, and that's 6 electrons plus 6 electrons gives us NH3. Again, this is reduction. Next we have aluminum. Gives us AlO2 minus plus 3 electrons. This is oxidation. So we see we have one nitrogen. It's balanced, one aluminum, it's balanced. So now we need to balance the oxygen. So NO2 minus, we need 2 oxygens for the first one. And we have 2 oxygens on the products for the oxidation half reaction, so we need 2 oxygens on the second one. Okay. Now we balance the hydrogens. We have 7 hydrogens, so we need 7H plus on this side. And we have 4 hydrogens, so we need 4 hydrogens on this side. Now we need to balance the electrons. So this is 6 and 3. We need to multiply this one by 2. And we get, so let's write the other one. Now we write the second one. And notice that the overall charge is 0 on both sides for the reduction half reaction. And it is 8, 0 for the oxidation. So now we need to cross out like terms and add the 2 reactions. So 6 electrons, 2H2O, get rid of 2 of those, 7H plus, we have 1H plus left. So our resulting reaction is 2H2O plus 2Al plus NO2 minus yields 2AlO2 minus plus NH3 plus H plus. Now, since this is in a basic solution, we have to add the number of hydroxides on both sides to balance the H plus. So since there's an H plus here on the product side, we got to add 1 OH minus. And since we add 1 OH minus on that side, we have to add the same on the reactant side. Now, so what happens? Well, now we get OH minus plus 2H2O plus 2Al plus NO2 minus 2AlO2 minus plus NH3 plus H2O. Now, this H2O will cancel out with one of those H2Os. And now you get OH minus plus H2O plus 2Al plus NO2 minus to AlO2 minus plus NH3. You see that the aluminum are balanced, nitrogen's balanced 2, 3, 4. Oxygen is balanced, and hydrogen is balanced. So this is the correct balanced redox reaction. So we just do one extra step at the end when we're dealing with a basic solution. Got one more example, and that'll conclude today's this lecture for this session. I'm actually going to divide it into two parts. It's been like an hour, so I know y'all are kind of long-winded, but I have to be very detailed. So the last example, we want to balance this reaction in a basic solution, so we got to determine the charge of each species. So here again, oxygen -2, manganese is going to be a +7. Here with manganese disulfide, sulfur here is a -2, and that's going to be a +4 for manganese, because sulfide is a -2 charge. And then of course sulfur solid is 0. So sulfur is oxidized, manganese is reduced. So we write our reduction. We got MnO4 minus plus 3 electrons gives us MnS2. All right. So that's the reduction. Now the oxidation. Gives us that. Let's go see how we do on this. So we have 4 oxygen. We need to put 4 H2O. Again, this is oxidation down here. And then we're going to put, I know I'm ignoring that 2S2 right now. You'll see where I'm going with it in just a second. 8H 8H plus. Undo. Guess I saved the hardest one for last. 8H plus. Okay. So now we need to multiply the top one by 2, the bottom one by 3. May have to redo this, but we'll go see what we get. We get 16 H plus 2 MnO4 minus plus 6 electrons, 2 MnS2 plus 8 H2O. Then we're going to get 3 S2 minus yields 3S plus 6 electrons. We gotta come back. Made a boo-boo. Let's see. Oops. Let's just start again. So we have the reduction, MnO4 minus plus 3 electrons gives us MnS2. S2 minus gives us S plus 2 electrons, S solid. So we need to balance the S here, so we're going to add 2 sulfides. Yeah, do that. That's what I think I forgot to do last time. All right. Now we're going to balance the oxygen. So we have 4. We need plus 4 H2O. We need an 8 H plus. Okay. So now let's see. That is -4. Okay, that's 0. All right. So this is, yep. So now we're going to multiply this by 2 and this by 3. So what do we get? Let's see. Let's see if we did this right. 16H plus 4 S2 minus plus 2 MnO4 minus plus 6 electrons gives us 2 MnS2 plus 8 H2O. Alrighty. And then we get 3 S2 minus 3 sulfur plus 2 electrons. This gives me 6. Now we're going to cross out what's the same on both sides. In this case, it's only the 6 electrons. So we get 16H plus 7 S2 minus plus 2 MnO4 minus yields 3S solid plus 2 MnS2 plus 8 H2O. Alrighty. Whew. That was a doozy. So now what we need to do is, since it's in a basic solution, we got to add as many hydroxide ions as we have H plus. So since we have 16H plus, we got to add 16 OH minus. There we go. And we're going to add 16 OH minus on this side as well. And so this becomes now 16 H2O plus 7 S2 minus plus 2 MnO4 minus yields 3s solid plus 2 MnS2 plus 8 H2O plus 16 hydroxide. So now this 8 will cancel out and this will reduce back down to 8. And so finally, sorry this was a little bit longer than I anticipated, 8 H2O plus 7 S2 minus plus 2 MnO4 minus equals 3s solid plus 2 MnS2 plus 16 OH minus. Now if we check everything, we got 7 and 7, 2 and 2. We got 8 and 16, 16, 16. Yep, that's balanced. So this is the correct balanced equation. Again, what I forgot to do the first time we did is I forgot to balance the sulfur by putting 2 sulfides in it. And the reason it's sulfide because there's no change in sulfur's oxidation number. So on that note, that concludes the session on introducing electrochemical cells and balancing redox reactions. The next part will be involving calculating cell potential for the different types of electrochemical cells. So on that note, I hope you enjoyed today's lecture. If you liked the lecture or learned something new, make sure you hit the like button. And Dr. Armand signing off. Until next time.